We're going back to the moon, but not as you remember. When people hear that we're going back to the moon, they imagine something familiar. Astronauts landing, walking across gray dust, planting flags. A repeat of history. And in a way, that's true, because Artemis III will mark the first human landing on the moon in over 50 years. But the moment you look closer, you realize something important. This is not Apollo, not even close, because we're not going back to the same place, not the same terrain, not the same conditions, not even the same kind of environment. Apollo missions landed near the lunar equator, flat regions, well-lit, relatively predictable. Chosen for safety, chosen because we didn't know what to expect. Artemis III is doing the opposite. Instead of going where it's easiest, we're going where it's most uncertain. The lunar South Pole, a place no human has ever visited. A region filled with extremes. Permanent shadows, extreme cold, unmapped terrain. Why take more risk? Why not return to proven locations? Because Artemis III is not about repeating the past. It's about building the future. And the South Pole offers something no other region does. Resources. Specifically, water. And that changes everything. Because water means sustainability. It means longer missions, permanent presence, fuel, air. The moon stops being a destination and becomes a base. It's a version of it we barely understand. And that's why this mission matters. Not because we're going back, but because of where we're going. When we think about the moon landings, we picture the same kind of place. Wide, open terrain, flat ground, clear visibility. That's not a coincidence. The Apollo missions were designed around safety. Landing on the moon had never been done before. So NASA chose locations that reduced risk as much as possible. Near the lunar equator, regions that receive regular sunlight, minimal shadows, relatively smooth surfaces. Even then, it wasn't easy. Astronauts had to manually adjust their landings to avoid hazards. The terrain was still unpredictable, but compared to the rest of the moon, those sites were the simplest option. And that's important, because it shaped how we think about the moon. We saw one version of it, the safest version, the most accessible. But it wasn't the whole picture. Far from it. Because most of the moon is nothing like those landing sites. And nowhere is that more true than at the poles. The lunar South Pole is completely different. The sun never rises high in the sky. That creates extreme contrasts. Some areas are in near constant light, others are in permanent darkness. Not for days, not for months, for billions of years. That changes the environment entirely. Temperature, visibility, surface conditions. Everything becomes more complex. Apollo didn't deal with that. It didn't need to, because the goal was to prove we could land and return, not to explore the most difficult regions. Artemis III is doing the opposite. It's targeting one of the most challenging places on the moon, a region we've only observed remotely, never experienced, never tested with humans. So when people say we're going back to the moon, that's not really accurate. We're going somewhere new, a part of the moon that Apollo avoided, not because it wasn't interesting, but because it was too uncertain. And now that uncertainty is exactly what makes it valuable. The lunar South Pole is not just another location. It changes the entire mission, because for the first time, we are not choosing a landing site based on simplicity. We are choosing it based on what it can provide. And that comes down to one thing: resources. At the South Pole, conditions are unique. The angle of sunlight is extremely low. The sun skims the horizon instead of rising high overhead. That creates two types of regions: peaks that are almost always illuminated and craters that are almost always in darkness. This contrast is unlike anything at the equator, and it creates opportunity. Those constantly lit areas are sometimes called peaks of near-eternal light. They receive sunlight for most of the lunar year. That means continuous solar power, a stable energy source, something Apollo never had. But the real interest is in the shadows, because inside those permanently dark craters, temperatures drop below minus 200 degrees Celsius, cold enough to trap volatile materials, including water. This is where scientists believe water ice exists, not as a theory anymore, but as something supported by multiple missions and datasets. And that changes everything, because water is not just useful, it's transformative. It can be turned into drinking water oxygen for breathing, hydrogen for fuel, which means the moon stops being a place we visit and becomes a place we can stay. But accessing that water is not simple, because it's not sitting on the surface in clear, visible form. It's mixed with regolith, hidden in shadow, located in some of the most extreme environments on the moon. And that creates a challenge. How do you operate in a place that never sees sunlight? How do you land, navigate, work in complete darkness and extreme cold? These are problems we've never solved on the moon. And that's exactly why Artemis III is going there. Because the South Pole is not just a destination, it's a test. A place where we prove whether long-term exploration is possible, where we learn how to use local resources, how to survive in the most difficult conditions the moon can offer. And if we can do it there, we can do it anywhere. At the lunar South Pole, darkness is not temporary, it's permanent. There are craters where sunlight has never reached, not once in billions of years. Because the moon's tilt is so small, the sun never rises high enough to illuminate their interiors. The result is something extreme. A place where time behaves differently, where day and night don't cycle the way we expect, and where conditions remain unchanged for unimaginable lengths of time. Inside these craters, temperatures drop below -200 degrees Celsius, colder than almost anywhere in the solar system, cold enough to preserve materials indefinitely. That's why scientists believe water ice exists there. Protected from sunlight, trapped in darkness. But that same darkness creates a problem, because operating in it is incredibly difficult. There's no natural light, no solar power, no visual reference. Landing in these regions is not like landing anywhere else on the moon. You can't rely on sunlight to guide you. Everything depends on instruments, precision, mapping, and even then, uncertainty remains. The terrain is not fully understood. We have data from orbiters, high-resolution images, but they don't capture everything. Small-scale hazards, sharp slopes, hidden obstacles, things that only become visible when you're there. And then there's temperature. Extreme cold affects everything. Materials become brittle. Systems lose efficiency. Batteries drain faster. Even robotic missions struggle under these conditions. For humans, it's even more complex. Spacesuits must handle extreme thermal differences. Equipment must function reliably in an environment we've barely tested. And then there's communication. Some of these regions are shielded from direct line of sight with Earth, which means signals can be blocked, delays increase, systems need redundancy. This is not just a darker version of the moon. It's a completely different environment, one that combines multiple challenges at once: darkness, cold, isolation, uncertainty. And yet this is exactly where we're going. Not just unexplored, but fundamentally different. If there's one reason we're going to the lunar South Pole, it's this: water. Not as a possibility anymore, but as something we believe is really there, hidden in the darkest regions of the moon. And the implications are massive, because water changes everything about space exploration. Without it, every mission depends entirely on Earth. Every drop of fuel, every liter of oxygen, every resource must be launched from here. And that's expensive, limited, unsustainable for long-term exploration. But if water exists on the moon, that changes the equation completely. Because water can be broken down into hydrogen and oxygen. Hydrogen becomes fuel. Oxygen becomes air, which means the moon can support missions without constant resupply. It becomes a refueling station, a base, a starting point for deeper missions into space, Mars, asteroids, beyond. But accessing that water is not simple. It's not a lake, not a visible ice sheet. It's trapped, mixed with regolith, frozen into the ground, hidden in shadow. Extracting it requires technology we're still developing: drilling, heating, processing, all in extreme conditions. And we don't fully know how concentrated it is, or how easy it will be to access. That's part of what Artemis III will help determine. Not just whether water is there, but whether we can use it, And that's a critical difference, because finding water is one thing. Using it reliably is another. There's also another factor: purity. If the ice is mixed with dust and other materials, it may require complex processing, more energy, more infrastructure, more systems that need to work perfectly. And again, this is happening in one of the harshest environments on the moon. Extreme cold, limited sunlight, difficult terrain. So while water is the opportunity, it's also the challenge, because everything depends on it. If it's accessible, stable, and usable, the moon becomes sustainable. If it's not, then long-term plans become much more difficult. And that's why this matters so much. We're not just going to the moon to explore. We're going to test whether it can support us, whether it can become part of a larger system of exploration. Because if we can use resources there, we change how we move through space. And it all starts with ice hidden in the darkest places on the moon. The lunar South Pole is valuable, but it's also one of the most dangerous places we could choose to land, because everything that makes it important also makes it difficult. The terrain is uneven. Unlike the relatively flat regions of the equator, the South Pole is filled with craters, ridges, and steep slopes. Landing there requires precision. A small error, and the margin for correction is limited. Then there's lighting. At the poles, the sun stays low on the horizon. That creates long shadows. Areas that look safe from orbit can hide hazards: rocks, cliffs, uneven ground. And in permanently shadowed regions, there's no light at all, which makes navigation even harder. Then there's temperature. Extreme cold in shadowed areas, relatively warmer regions nearby. That creates thermal stress. Equipment must handle rapid changes. Materials expand and contract. Systems are pushed to their limits. And then there's communication. The moon's terrain can block direct signals to Earth. Some regions have limited visibility, which means communication may rely on relays. Additional systems, more complexity, and every added system is another point of failure. Radiation is constant. There's no atmosphere to block it, no magnetic field to deflect it. Astronauts are exposed continuously, and unlike Apollo, this mission is not designed to be brief. Even short stays in this environment require careful planning. And then there's dust. Fine, abrasive, electrically charged. It sticks to everything. Damages, seals, interferes with equipment. It's not just inconvenient, it's a long-term problem. When you combine all of this, you don't get a simple landing site. You get a high-risk environment, one where every system must work, where every assumption must be correct. And that's why this mission is so different. Because we are not choosing the safest place. We are choosing the most challenging one. At first, Artemis III sounds like Apollo 11 repeated. Land on the moon, step outside, make history again. But that comparison doesn't hold, because the mission itself is fundamentally different. Apollo was designed for speed. Reach the moon, prove it could be done, return safely. Short missions, minimal infrastructure, limited objectives. Artemis III is not doing that. It's part of a system, a larger plan that goes beyond a single landing. Because this time, we're not just visiting, we're starting something. The mission is connected to multiple elements: the Orion spacecraft, the Space Launch System, the Lunar Gateway, a human landing system. Each part plays a role. Each one must work together. This is not a standalone mission, it's an integrated operation. And that adds complexity. More systems, more dependencies, more variables. But it also adds capability. Because Artemis III is not just about reaching the surface. It's about what happens after. Exploration, resource testing, longer stays. Activities that Apollo was never designed to support. There's also a shift in who is going. Artemis III is planned to land the first woman and the next man on the moon. That's not just symbolic. It reflects a broader goal: expanding access, expanding participation, turning lunar exploration into something ongoing. Not a single moment in history. And then there's the location, the South Pole. Everything we've discussed leads here, a place more complex than any Apollo site, more demanding, more uncertain, which means Artemis III is not just repeating the past, It's redefining what a lunar mission is. Artemis III is not the end goal. It's the beginning. Because the real objective is not a single mission. It's a presence, a sustained human presence on the moon, something we've never done before. Apollo proved we could reach the moon. Artemis is trying to prove we can stay. And staying requires infrastructure, power systems, habitats, communication networks, systems that can operate continuously, not just for days, but for months or years. That's where the South Pole becomes important. Constant or near constant sunlight in certain areas provides energy. Water, ice provides resources. Together, they make long-term operations possible. But building that system is not simple. It requires testing, iteration, understanding how everything works together in a real environment. That's why Artemis missions are structured in phases. Each mission adds something: more data, more capability, more confidence. And Artemis III is a key step. It transitions from preparation to presence. Not a full base yet, but the beginning of one. A foothold. Something that can grow over time. The moon becomes more than a destination. It becomes part of our infrastructure in space. This isn't just about returning to the moon. It's about what comes after. Because the moon is not the final destination. It's the starting point. Everything we learn there applies to something bigger. Mars. Deep space missions. Long-term human exploration beyond Earth. The moon is close enough to test systems, far enough to challenge them. If we can build a sustainable presence there, we prove that it's possible elsewhere. But if we fail, that tells us something too. That we're not ready yet. That our assumptions need to change. The moon becomes a checkpoint, a place where we test not just technology, but our understanding of space environments. And that's why Artemis III matters. Not just for where it lands, but for what it represents. From exploration to expansion. So yeah, we are going back to the moon, but not to the place we remember, not to the safest regions, not to the simplest terrain. We're going somewhere new, a place of darkness, of extremes, of unknowns. Because this time, the goal is different. Not just to land, but to stay, to build, to understand, to prepare for what comes next. Artemis III is not a repeat of history. It's the start of something new. And where we land is what makes all the difference.